Hello and welcome to the second training on SWOT data access in Madagascar. My name is Merritt Harlan. I'm a researcher with the U.S. Geological Survey in the Hydrologic Remote Sensing branch, and today I'm going to be talking about Surface Water Ocean Topography, or SWOT, satellite data access in Madagascar using Application Programming Interface Services, or APIs. As an overview of today's talk, I'm going to be talking about how we can access the SWOT prior river and lake data, which allows us to view the geometries that we're interested in downloading data for. And then I'm going to demonstrate different ways in which we can access SWOT time series data using the Hydrocron API. And finally, I'll end with some examples of how we can batch process SWOT time series data in order to download data over several lakes or rivers at once. And here's an example of a graph I showed from last time of the Akupa River and a time series of water surface elevation from the SWOT satellite. And so today I'll be showing how we can download this type of time series data across several different platforms. This training is a follow-on from part 1 of the series, in which I talked about accessing SWOT data on web platforms, which you can check out at this YouTube link shown here. I'm going to focus today on application programming interfaces because it allows us to access SWOT time series data for many rivers or lakes at once and is also quite efficient. There are some limitations with using this API. For one, it requires internet access as well as compute power, and it requires some programming. And this API service that I'm going to be using only contains the river single pass and lake single pass prior data. And so we aren't going to be able to access pixel cloud data or SWOT raster data through this service. And at this time, there's still only the prior lake data, not the unassigned or observed lake data, which looks at water bodies that haven't been previously defined in this lake database, which I'll talk about shortly. The SWOT river database defines high-resolution river nodes, which are points along a river centerline spaced every 200 meters, as well as river reaches, or longer segments up to 10 kilometers of a river, in either shapefile, GeoPackage, or NetCDF formats. The SWOT river database, or SWORD, contains hydrologic variables accompanying these river geometries, including an estimate of the water surface elevation, river width, river slope, as well as other parameters for global rivers that are 30 meters wide and greater. This database can be explored at the SWORD Explorer website, which I've linked to here, and more information is available through this publication shown here. And now I'll transition to demonstrating how we can use SWORD Explorer to access this data over Madagascar and download it for use with the API service. For accessing SWOT river database data, we're going to first click on Africa if we're interested in the Madagascar river reaches. And I'm going to select Basin 18 here to select the Madagascar river reaches. And it may take a few moments to load. And now we can see the river network on the island of Madagascar. And if we click on a given river reach, we can see information about that river. We can also visualize the river reaches, for example, by their water surface elevation or the river width. And we can also view parameters of a given river reach in these plots down below. Now, we may want to access this data locally. For example, if we want to get a list of all the reach IDs that are in Madagascar. And in order to do this, we're going to want to download the data set. And SWORD version 17b, which is the version we're looking at here, is the official version for SWOT version D, river single pass vector products. SWOT version D is the latest version of SWOT and is available through roughly this May going forward, but it will be back processed for the full SWOT record. However, if we're interested in historic data at this time, We may also be interested in SWOT version 16. So we're going to download both of these versions as well as this translation file. And any of these formats work. I'll be working with GeoPackage for today. So we'll download version 17B as well as SWOT version 16. And this version 16 to version 17B translation so that we can pair these two data sets together. And we'll save those files locally, and then we'll view them in a software called QGIS that allows us to visualize these data. Now that these data have finished downloading them, I'm going to open a software called QGIS, and this is just a blank project, which we can do from doing project new here. And I'm just going to drag in the files that I'm interested in viewing. So we're going to go into the GeoPackage folder and look for AF, short for Africa, _ SWOT reaches version 16. And drag that on in. And here we'll see all of the SWOT river reaches on the continent. I'll also drag in version 17B. And then the translation file that we also downloaded is just represented by a comma separated values, not necessarily a spatial format. I also encourage folks to check out the SWOT product description, which contains more information on this database, including what changes have occurred over time, and also more information on the source data sets and the parameters that we see within it. Now, in order to crop the river reaches to Madagascar, there are several different ways to do it, but we're going to create a geometry to crop these river reaches to. And so in order to do that, we'll go into Layer, Create Layer, and I'll create a new GeoPackage layer and name it MG bounding box, which we'll say is a polygon. And then we will toggle editing and add a polygon feature. And I'm just going to draw a box around Madagascar. And then turn off toggle editing to save the layer. And so now that we have a rough bounding box, I'm going to clip the reaches to this box. We could have also uploaded a shapefile of Madagascar or drawn a smaller bounding box if there's a different region we're interested in or a given basin, for example. In order to crop these two layers to this area, we'll go to Vector Geoprocessing Tools Clip, set the overlay layer to this bounding box, and save to a new file. So here we'll say MG SWOT version 16. And we will do the same with version 17 data. All right, and now we have the version 16 and 17 output shown here. And they're quite similar, but some of these reach IDs may have changed, which is why we want to download both versions. For the prior lake database, we're going to access this data through the HydroWeb Next platform, which I demonstrated last time. And the lake database defines high-resolution lakes and reservoirs that the SWOT satellite is estimated to observe. And similar to the SWOT database, the Prior Lake Database, or PLD, contains hydrologic variables, including water surface elevation, area, and so forth for global lakes and reservoirs. Again, we'll access this data through the HydroWeb Next platform, which I'll demonstrate now. And you can also read more about this data set and its many attributes in this publication linked here. Now I'll demonstrate how we can download data through HydroWeb Next to get the Prior Lake data. And first we'll want to log in. And once we log in, we'll be able to access this download feature. And so I'm going to search for the SWOT Prior Lake database. And I should note that we can also access the SWOT Prior River database, or SWORD, here as well. And so we're going to add the river database to our project as well as this lake database. And now we can see both layers here. And I'm going to make sure for where that we're just looking for data over our map view here. And I'm going to make sure that we can see the SWOT Prior Lake database on our menu here to the right. And then I'm going to click Download. Within this period, and it will be any time, and we can now click Order Product. And again, this is quite a large file, and so we can check on our download process within the Download Center here. Now that we've downloaded the Prior Lake data, we see that there's actually a couple of different basins that we've selected. But if we remember from the SWOT River database, Madagascar is related to Basin 18, so we're going to select this file. And there's a bunch of different data products within the Prior Lake database. So we have basin, lake, lake catchment, lake influence, and past tile. For our purposes, we're mainly just interested in this lake version, and so we'll add that layer to our graph. And we'll see all of the Prior Lake database over Madagascar pulled in here, as well as some surrounding islands. And so we're going to save this file by exporting it, and we'll save it to the same area here, Madagascar PLD. And now we have several files that have the SWOT River database as well as the Prior Lake database over the area of interest for us. Now that we've learned how to download the SWOT Prior and River databases, we're going to now jump into the Hydrocron Application Programming Interface, or API. And an API is a service that allows an end user with a browser, for example, to make a request, and the request goes through the API service, which interacts with a server backend system to download or access the data. And then a response is returned to the user, which often contains, in this case, the satellite hydrology data. And so Hydrocron is an API that repackages hydrology data sets from the SWOT satellite into formats that support time series analysis. And so currently, to download data directly through NASA, you have different shapefiles for each river overpass, but instead we may be interested in time series data that we can open through a tabular form, for example. And so these API calls can be made via internet browser, or for example through Microsoft Excel using Power Query, or programmatically through R or Python, for example. And there's a lot of different documentation on both how to use APIs and how to use this specific Hydrocron API, which is developed by PODAC, the Physical Oceanography Data Archive Active Center, which I've linked some information here. recently there was also a webinar that went into depth on how to access and visualize and analyze SWOT data using this API, which I encourage you to check out for more information as well. So let's dive into Hydrocron by first looking at the documentation page available at this link here. And we'll start by looking at some examples. And I should mention that there's a lot of information on the site, so I encourage you to check it out. And there's a couple of different examples that walk us through how we can change the input parameters to get different outputs. So for example, we can get a time series GeoJSON, which is a spatial file for a river reach. Here we're mainly interested in the time series in tabular form, so we're going to scroll down to getting a time series, comma separated values file for a river reach. And so we can also access an API through clicking on a link directly. And so if I open this link, for example, in a new tab, we have a status that means that it went through, so it's 200 or okay, and it returns the time as well as the number of timestamps. And so here we have our comma separated values format where we see the reach ID, the time string, the water surface elevation, slope, the units, and slope units. Now if we wanted to change this call, we can do so directly in the browser. For example, we can set the start time back earlier and end time to be later. And we can also add width as well as reach quality if we're interested in that data as well. And now we see new data being returned that has the reach ID, time string, water surface elevation, width, slope, and reach quality, along with the units for this data as well. And we see a longer format because we've requested a longer time series. So this is one way to use it. Accessing these data is a little bit tricky, but we could, if we wanted to, copy and paste this information into a browser to view it there. And this is just one of the many examples on this site. And if we're interested in using it programmatically, there's also a lot of resources in the tutorial that relate to using these calls within Python as well. Now there are also other ways to use this API other than the web browser. So one example is in Microsoft Excel. In version 2016, we have something called Power Automate, which allows us to get and transform data, including from the web. And so here we can use a URL. So for example, we can use this URL that we used previously, and we'll paste it on in. And here we are querying SWOT data through Hydrocron for a reach feature ID, and we have an output of a CSV, a start time of January 25th, 2023, an end time of August 5th, 2025, and the fields we're looking at are reach ID, time string, water surface elevation, width, slope, reach quality. And if we click OK, we're going to see the Power Query Editor pop up. And again, we get the 200 OK status, meaning that our API request was successful. We have the time it took and the number of timestamps returned. And we can view the data in this record here. And to make it easier to view, we're going to drill down and convert it to a list. And once we do that, we can then convert it to a table. And the table columns will be separated by a comma. And one final change is that we're going to use our first row as a header. So now we have this output in a nice tabular format. And we can close and load this into Excel now. And here we'll go through the same process where we're querying the API and getting the return here. Now, what if we wanted to change this initial request? We can edit this workflow and go back up to this source. And say, for example, we wanted to add water surface elevation uncertainty, or WC_U. And also, what if we wanted to make sure we were looking at a river reach in Madagascar? So here I'm going to click on this info to view the data layer, and I'll look at version 16 SWOT data. And we'll select this reach here on the Betsy Boca. And so we want reach ID up here. So I'm going to copy that and paste that feature ID into Excel. And then I'll press this check mark. And we will again close and load the data to view this time series here. So now we have data for this reach ID, and we see the different parameters we've requested here. Now for the time string, if it says no data, that means the values that observation was not valid for one reason or another. And so the default null value will be this minus 999999 and so forth. And so here we'll sort to unselect no data to just see the full time series. And here we can easily share or start to analyze these data within Excel directly. All right, now we are going to introduce how we can access SWOT data through the Hydrocron API in R. And here I'm using RStudio, but you're welcome to use any IDE that you prefer. And if your screen looks a bit different from me and you're using RStudio, here I've created a new file called an R script, and I'm working off of it here. And I'll just be coding from this blank script, but I can also share this file if you're interested in following along. And so first I'm going to load in some libraries that we will need to make this API call, including HTTR, JSON Lite, dplyr, and string R. And if you do not have any of these packages downloaded beforehand, you can use the install packages command, and you'll likely want quotations around the package name to install these packages. I will likely not restart R because I've already loaded these packages. And so now that we have the libraries, we're going to write a function to get SWOT reach data. And we'll make this function have a couple of different input parameters, including a reach ID, which we can access through our, let's see, we're looking for version 16 reaches here. And so if we click, we can get a reach ID that might be of interest. And in addition to a reach ID, we'll also query the start date, which we can set to January 1st, 2023. And here the format generally goes month and then day, as well as an end date, which I will set to today's date. Finally, I'm going to specify which fields we are interested in. We can view these fields by clicking on the user guide under fields here, and we can see the different field options for the reach data, the node data, and the lake data. I am going to select reach ID time string water surface elevation slope, width, and reach quality as the variables I'm interested in. And then within this function, we're going to try to recreate the URL command that we used on the web interface. So I'm going to go ahead and paste together this URL. And I'm going to chop it up based on which inputs we're interested in changing. And so this includes the feature ID. And so here we will paste in the reach ID instead. And I'm also interested in changing the start time, which we will replace with start date. And the end time, which we will replace with end date. And then finally the fields. And so now we have a pasted URL that recreates the version here, but now we can change any one of these input and it will change our URL output. So now that we've crafted this link, we now have to make a GET request in order to access the data, which we will use with the GET function. And we are going to check to see if our status code looks good, and that would mean a response of 200. And then we're going to read in the response text if our status request is good, and we are going to change the output to a character and look for the content because that contains the data that we are interested in. And so we'll use the read CSV command to access this content. False. And this is optional, but we can also filter out which time strings are not valid so that we don't have that data included. And then if our data has valid rows, we're going to go ahead and return it. Oops. So essentially this function recreates the URL, makes a GET request, and returns data if it's valid. So let's test it out. One nice thing about this function is that we don't necessarily have to change anything. And so in order to run this code, we're going to go ahead and highlight it and then press run. And here we're making the command to get the reach data. And if we view it, we can see the output of the reach ID, time string, water surface elevation, slope, width, reach quality, and units displayed nicely. We can also save this data to a CSV through that command, and we can also load in another library to plot the data. Reach data. And on the x-axis, we will put the time string, and on the y-axis, we can put water surface elevation, and we will plot this data as a point and add some x-axis labels as well as y-axis labels. Elevation. And so the plot will look something like this, where we have water surface elevation on our y-axis and date on our x-axis. Now say, for example, we are only interested in data that has a reach quality of 1, meaning better data. We could filter the data here So that reach quality is less than 2. And we can plot this and see what we're left with there. And so far we've written this function to query reach data, but we could make it more generalized and change the URL slightly so that we have new variables such as feature ID equals reach and that might allow us to look at other data that's not a reach as well. And actually I'm going to call this SWOT data so that I don't confuse it with the other feature IDs. So say, for example, now that we have this more generalized function, we can use it to also access node level data or lake data. And so in order to access lake data, for example, we can call a new function, get SWOT data, and SWOT data is going to be prior lake, and the SWOT ID will now be one of the lake IDs. For example, this lake ID is here. And we're also going to need to change the fields to instead return lake ID, time string, WSE, and total, or area total rather. And if we view lake data, now we'll get a time series of that given lake. So I hope this was, a helpful, quick overview of some ways in which we can use R to access this data. And later on, I'll give some examples of how we can adapt this function to download data over multiple lakes or rivers at once. All right, moving on to the Python version of this tutorial. We're going to be basing this off of the tutorial documentation within the Hydrocron site. And here they've provided some explanation as well as code to reproduce 2 different examples, one being displaying a river reach on a map using the GeoJSON type output. And so we'll create a map that looks something like this for a given river reach. And the second example is analyzing a time series of a river reach using the comma-separated values or CSV output. And in order to run this code, I've chosen this Jupyter Notebook Python GUI, and I've just copied and pasted each of these code blocks over to this notebook here. And you may need to install some of these modules within Python as well. And first I'll just go through the tutorial as is, and then I'll give some examples of changing the feature IDs to focus on rivers in Madagascar, for example. And so to get data from Hydrocron, we're going to call the same URL that we used within our Excel and R tutorials. And here we see a positive OK status of 200, the time it took for the response, as well as the number of observations returned within this time frame, which is between January 1st, 2024 and March 30th, 2024. And here we see a pretty long output because this includes the geometry coordinates of each observation, and that is because we've requested that our output be in GeoJSON form. Now we will extract that GeoJSON data in order to get these latitude and longitude coordinates shown here. And finally, we'll use this Folium package in order to plot the river reach. And this plot is zoomable as well, and we can also click on features too. All right, moving on to our second example for the time series analysis. Again, we're going to call this hydrocron URL, but this time you'll notice our output is CSV, comma separated values, so we don't get nearly as long a return because the geometry portion is null. And we can query the results and CSV portion of this output, which we'll notice comes from these two here, and this will just return that data in comma separated values format, which we can then visualize within this data frame. In order to plot the time series, we'll convert that time string to a datetime object using the pandas library. And finally, we will plot the water surface elevation for this given river reach. Now, say we wanted to instead look at a river reach in Madagascar. Similar to in R, we can kind of go and find a reach that we're interested in. Here I'm in QGIS, where I'm looking at a map of SWOT version 17 reaches, and I'm going to select this reach ID for this reach on the Betsiboka, and we're going to go ahead and paste that reach ID in here. And because this reach is from SWOT version 17b, we're also going to want to use the latest version of SWOT data, or the version D data. And we can call this through the collection name parameter here. And so I'm going to add collection name equals and paste in version D. And then I'm also going to update the feature ID. Additionally, we're going to change the time stamp to cover all of the SWOT observable period, so from 2023 up until present. And for the return fields, we'll still look at reach ID, time string, water surface elevation, width, and geometry, but those could be changed just as well. And so now when we run this, we get, again, a good response and 18 results back. And we'll see the new geometry pasted here. And again, we'll extract those coordinates and update our map plot to show this reach in Madagascar. All right, so say we wanted to make these same changes for the time series analysis. For simplicity, I'm going to go ahead and copy and paste my new collection name as well as feature ID here. And we're going to call this again. Oops. And feature ID. Oh, and here I forgot to update the time frame again, so I will do that as well. And something to note here is that version D data might only be available beginning in 2025, and so one of the reasons for that error might be that the timestamp ended in 2024 there. All right, so now we get an OK response, and we can look at the CSV output of these data. And here we are seeing a couple of no data values here. And so here, well, we will first have to kind of filter those out before we can continue plotting. And so to fix this data frame, we are going to filter out instances where the time string value is null. And so now our data frame will look like this, and we should be able to convert to time string and then plot our water surface elevation profile here. So this is just one example of working in Python, and I hope you all can take some time to check out different ways to change the data, for example, by adding more variables to return or testing out the lake data and so forth. And you can also follow along if you'd prefer directly from this tutorial page, or check out the GitHub repository as well for more examples or to add an issue if you have any questions. So far, all of our examples have been focused on downloading data for one river reach or node or lake at once. But we can also use the Hydrocron API to download SWOT data over multiple areas at one time, scaling all the way up to all of the rivers or lakes in Madagascar or even globally. To do so, we need to make multiple API requests, ideally using parallel computing. And so instead of sending a bunch of requests at once, we can send different requests in batches, which we're showing here. And I'll demonstrate this now using some tutorials within Python and R. Similar to our last Python tutorial, here we are also going to use an already generated bit of Python code to download SWOT time series data in parallel. And this tutorial is hosted on the PODAC cookbook site, and it can be accessed under tutorials, dataset specific, under the SWOT access and visualization for the Hydrocron time series. And this tutorial is written by Nikki Tibaldi and Cassandra Nichols. And so here I'm going to go ahead and copy all of this code into this notebook within Jupyter Notebook, and we'll run through it together. So here I'm importing different libraries, and in this next bit of code I'm going to specify a number of workers in order to download data in parallel. Depending on your machine, you might be able to increase this number or potentially decrease it as well. And here we're going to assign URLs for the Hydrocron API as well as the feature translation service, which will allow us to query reach IDs based on a basin identifier or a river name, for example. And here we will define this query feature translation service and return the number of reaches based on these identifiers. So here, just following the tutorial, we're going to look for reaches within that basin and find the total number of non-duplicate reaches. For the sake of speed, we will just look at the first 10 reach IDs, but we could look at all of them, for example, by just commenting out the subsetting by 10. Now we are going to query Hydrocron, and this function is pretty similar to the one that we set up in R, where we have the base URL, the reach ID that we're interested in, the start and end time, the fields that we want, and an empty data frame as well that we can pass in. And so now we are creating this query with a start and end time as shown here with the fields there as well. And so this might take a little bit since we're querying data over all of those reaches. So about 9.81 seconds wall time. And we do see that, there's a couple of no data values for the time strings, which we will filter out here as well. And so now we're left with a clean data frame, and we can create a line plot of all of these different reaches within this bit of code. Which might also take a couple moments to plot each of those reaches. And here we have different reaches within that basin and the water surface elevation time series for all of these. And finally, we can close out the client so that we don't stay in this parallelized environment. All right, so similar to last time, I wanted to give an example of how we might update this. Say, for example, if we wanted to change the basin identifier. So here I'm going to search for the Betsy Boca River and rerun this bit of code. And instead of querying by basin this time, I'm going to query by river name. And actually, let's also add in the ability to look at version D data. And so that would be hydrochron this river data version here. And so we'll add collection name equals that. Okay. We'll see if that works for us. And so now we are querying these reach IDs that have the name Betsy Boca, and again, we'll just keep the first 10 reaches that show up. You might notice the river name might take a bit longer to search since we have to go over a wider region. And here, let's change the end date again, since we're now querying version D data as well. All right, great. So we get a couple of returns for these sites, and the reach IDs show up as in Madagascar. And here we will filter out our null data values and then plot the time series. And so unlike before, here we're able to query data over many reaches at once, and we could also, type in different river names as well to get different regions, or up the number of reaches that we process at one time. But here we are accessing water surface elevation time series for 10 of these reaches all at once. And that's it for the Python parallelization tutorial. And next we'll go into the R stuff as well. Thank you. To wrap up the tutorial on batch processing of SWOT data, I wanted to also revisit the hydrochron example in R that I gave. And so here's the function that we wrote to download SWOT data for a given reach. And then we showed an example of downloading data from a prior lake and plotting the water surface elevation for that lake. Now I wanted to transition to talking about how we could adapt this function that we wrote for batch processing. And so I'm going to bring in two more R packages, SF, which allows us to interact with the spatial data we created earlier, as well as feature apply, which allows us to use parallel processing. And I'm going to read in the SWOT River database version 16 reaches for Madagascar. And these data represent the reaches that are on the island of Madagascar. So let's see if we could plot them as well. And so we have varying reach IDs within that basin, and as well as the geospatial data too. And so in terms of our function to batch download SWOT data, we're going to read in not one ID, but multiple SWOT IDs. And again, we'll have the option to change reach, prior lake, or node, as well as the start and end date, which I've updated to today's date. We also have the option to change the fields, and similar to in Python, we're going to specify a core count, which in this case, I've detected the number of cores on my machine and subtracted 2. This line here sets up a multi-session threaded environment with the number of cores specified. And here I'm going to call a function futureApply on the SWOT IDs, and I'll call the function getSWOTData and pass in the parameters of the SWOT data type, as well as the start, end date, and the fields. Finally, I will bind all of the different reach ID data together, or lake or node ID, and then I'll check to see how many of the IDs I specified have been successfully downloaded. And finally, we'll return the data frame and remove the multi-session environment that I created. And so what this looks like, for example, for the first 10 reaches within the Madagascar SWORD version 16 data, is we will download these data in parallel for those specified reaches, similar to in our Python environment as well. This will take some time to set up the code and to actually query the data. And if we look at this data frame, we see the reach ID, time string, water surface elevation, slope, width, and reach quality, along with the units for each of those data sets. And we have multiple of these reach IDs within this data as well. So if we wanted to, we could expand the number of reaches that we look at. It will take time to download data for the full data set, but here we can at least do it in a shorter time than changing reach ID by reach ID up there. Finally, I also just wanted to show, what if we wanted to add collection to this function. And so here I'll again go back and find the SWOT data versioning collection that I'm interested in, and I'll add up here, down here, and collection name equals collection, so that if we want to, we can specify the name of the collection to get the latest data. And so if we update our function here and update it here as well, we can check to see how much data we get for version D2. And so that would be messed up since I needed to specify the lake one. But here, let's update our initial function too, to look for reach data as well. Reach ID. And so there's our version D water surface elevation for this reach, as well as our version D information here. Collections not found. Oh. Assuming we can spell everything correctly. And so again, to get the different collections, we'll want to go to that page. And something actually that I should have updated is the reason why we see only 3 out of 10 successfully downloaded is what we need to do is actually change this to version 17. And so we will make sure to do that and update this function as needed, so that we're getting the appropriate reaches this time. Version D. And so if we rerun this bit of code now, we see that more of these reaches should be successfully downloaded. I recommend going forward to mainly kind of focus on the version D data, since more and more data is available. But if you are interested in more of a historic time series, definitely consider working with version C, since in this case the earliest date that we're seeing is around May of 2025. In conclusion, SWOT river and lake geometries can be found and accessed within the prior data sets that we linked to here. We can also download SWOT time series data directly through the Hydrocron application programming interface. And if we so wish, we can use parallel processing and programming to download data over multiple SWOT river reaches, nodes, lakes at once. Thanks so much for your attention. I've linked several of the resources used in this tutorial here, including those 2 Python tutorials, and we anticipate more trainings to come, but in the meantime, please don't hesitate to reach out with any questions or feedback. Thanks.